And welcome back, guys. Today we're going to be starting our last unit for Math 20-1, and that's Unit 8, Systems of Equations and Inequalities. In this unit, we're going to be looking at two main topics. The first one is systems of equations, and the second one is inequalities. Now, we're going to start off with systems of equations, and we're going to go over some things that you've already learned in Math 10C, and we're just going to continue forward with them in Math 20-1. So first of all, as a quick review, a system of equations is a group or a collection of two or more equations that have the same set of unknowns. And so that means their x value and their y value are the same. And if we were to take that x value and y value and sub them into each equation, it would make both statements true. So when we're solving a system of equations, we have to find values for each of the unknowns that satisfy every equation. So the only way to know that a coordinate or an answer is actually a solution is if those values of x and y make both statements true. Now, when we're solving a system of equations, we can solve graphically or we can solve algebraically. When we're solving graphically, the solution to a system is where the graphs intersect. And so looking back at grade 10, we looked at three different methods. We looked at graphing, substitution, and elimination. Graphing is what we call solving graphically, and substitution and elimination are both algebraic methods. So in addition to looking at how we solved systems of equations, we also looked more specifically at the number of solutions and the types of solutions that we could have. In grade 10, we looked just at linear equations, so we were looking just at straight lines or linear functions. And with lines, we have three possible sets of solutions. So the first one is no solution. If I have two equations that are parallel, in other words, they have the same slope, but they have different y-intercepts, they never cross or never meet, so there's no solution. If I have two equations that have different slopes, no matter how big the numbers, at some point they will cross. So there's one solution. So if they have different slopes, one solution. And then the last one was one that was a new term, and that was coincidental lines. And these were lines that had infinite solutions. So if I had two equations, even if they initially looked the same, looked different, when I simplified them down, if they were the identical equation, that meant that every point was the same, so they had infinite solutions. Now, taking a look at grade 11, we're going to be looking at both linear quadratic systems and quadratic-quadratic systems. The methods are going to be exactly the same as the ones that we did in grade 10. They're just going to be different functions. So starting off here, a linear quadratic system of equations is a linear equation, so a line, and a quadratic equation, so a line and a parabola involving the same two variables. The solutions to the system are going to be the points where they intersect. And so if I look at this system of equations here, I have x plus 2 and x squared minus 4. If I were to actually figure out those solutions, they intersect at 3, 5, and they intersect at negative 2, 0. So my solutions would be 3, 5 and negative 2, 0. Because there's two intersection points, I have two solutions. Now with a quadratic-quadratic system of equations, this is when we have two quadratic equations that involve the same variables. So in other words, I have two parabolas. And so the solution is going to be, again, where those parabolas meet. With this particular example, these ones are going to be decimal values, but we would cross at 1.73 comma negative 1, and it would cross at negative 1.73 comma 1. Now, if we were solving algebraically, we could get an exact answer, but today we're just focusing on the graphical solutions. Now let's take a look at the number of solutions or the possible solutions that we could have. Now taking a look at our linear quadratic equations, there are three possible types of solutions. So for the first one, we could have a parabola opening up, and we could have a horizontal line going somewhere below. These two are never going to meet, so there's zero solutions. Now this could also happen that we have the parabola opening down and the horizontal line is somewhere above. It would be the same idea, no solutions. We can have a line meeting a parabola at just one point. Okay, so right on that one point there, it meets, and that's called our point of tangency. For those of you that are taking physics, you're probably familiar with talking about tangents and having to find that point of tangency. So that means it touches the parabola just in one spot. So that would mean there is one solution. And our last possibility is that we have our parabola and our line crosses it in two different spots. And so in this case, we would have two solutions. Now, when it comes to quadratic-quadratic equations, we actually have 4 scenarios. So the first possibility is that we have no solution. So one parabola opens up, one parabola opens down, and we would have no solution. We can have one graph that's opening up, another graph that's opening down, and they just meet at one point. Okay, so they meet right there. This would be one solution. I can have two graphs that overlap in two spots. And so that would give me two solutions. And similar to the linear functions, if I have two identical graphs, so if I have one parabola and then another parabola that's the identical equation, if they overlap in every single point, then they would be called infinite solutions. Taking a look at our first example, a diver is doing training dives from a 3-meter springboard, and her coach uses video analysis to plot her height above the water. The question is, which system could represent this scenario? And then what does that intersection point actually represent in the situation? This might be a time where you can pause the video, take a look at the 4 graphs, make your decision, and then come back. All right, now taking a look at these 4 systems, our answer is system D. But let's take a more specific look at why that might be. So first of all, we're told that the diver is doing training dives from a 3-meter springboard. Well, if we take a look at all of these questions, they all have a point that's taking off above 0, but we need to look more specifically at the path of the diver. Now, with the first one here, we have a parabola, which would be the path of the diver. We have that as well for C and D. But when we look at the blue line would represent our horizontal distance at that 3-meter height, and that would represent our diving board. If we take a look at the first one, the light blue line is going down, so that would show that something is decreasing. System B, we have that blue line going across, but the darker blue line does not represent the path of the diver. And so then we narrow it down to C and D. Well, if we look at system C, the diver is taking off above the height of the diving board. So that doesn't make sense in the context of the question, making our answer D. So then the question is, what does the intersection point represent? Well, this diver is taking off. This is her height over time. So she takes off and then she comes back down. And this would be the point where she crosses that plane of the diving board, so that original 3-meter height. So as she takes off, she goes up in the air, comes down, and that's where she crosses that 3-meter point. All right, let's take a look at another similar example. Two divers start their dives at the same time. One diver jumps from a 1-meter springboard and the other jumps from a 3-meter springboard, and their heights above the water are plotted over time. The question is, which system could model this scenario? And again, explain what the intersection point means. So again, take a minute to pause the video and then come back and check your answers. All right, now in this case, our answer is system A. And so we take a look first again back at the question. We're told that one diver is taking off from a 1-meter springboard and one's taking off from a 3-meter springboard. Well, if we look at system B, one of the divers is taking off at 0, so that doesn't work. The next one, they're both taking off from 0, so that doesn't work. And this one here, it looks like they're taking off after time has already passed. And so this again does not make sense in the context of the question. All right, so system A makes the most sense. One's taking off at 3 meters, one's taking off at 1 meters. They come up into the air and then come down. Now, with the question about intersection point, these graphs don't have an intersection point during that domain. So during that time frame, there is no intersection point. So that means our divers don't crash into each other, which is probably a good thing. All right, so moving on, let's take a look at actually solving some of our systems of equations. So we're going to start off with a linear quadratic system. And so in this particular question, we're given the equations and we're asked to solve by hand. So solve graphically by hand. So we're going to actually graph our equations and find their intersection points. Now, in order to do that, we have to rearrange our equations so they say y equals. And then we can use for the linear function, we can use our slope-intercept form to graph, or we can create a table of values and plot our points as we go. So for the first equation here, we have 4x minus y plus 3 equals 0. We're going to rewrite that by moving the y, and we have y equals 4x plus 3. Now remember, when we're moving terms across the equal sign, they need to change signs because essentially we're doing the opposite operation. And so for our first equation, we have y equals 4x plus 3. For our next equation, we have y equals 2x squared plus 8x plus 3. Now, in order to graph these, again, you can use a table of values or you can use the slope-intercept form. For the first equation here, I'm going to plot at 3, and my slope is 4, so I'm going to count up 4 and right 1. And I can count down 4 and left 1. Now, as we're solving these equations, it's important that we use a straight edge and make sure that we have nice, neat lines, and that leads to accurate intersection points. All right, so we have the first graph drawn. We're going to take a look at the parabola. Now for the parabola, again, you can make a table of values. You can use your calculator for that table of values, but you need to plot the points, the main points like your y-intercept, your vertex, and so on, so that you have a really good idea about the shape of that graph and where it might meet the linear function. So for this particular graph, we have a vertex that's happening at -2 and -5. So again, I would have plotted these points or made a table of values. I have another point at -3 and -3. And -1 and -3. I have another point at 4, 3, or sorry, -4, 3. And I have another point at 0, 3. So again, this would have come from making a table of values. And then I can do a quick sketch of my graph. In this particular case, my x-intercepts would have been decimal values, so I'm not too worried about those. Now, as we do that, we can actually see that our graph intersects right here at 0, 3, and right here at -2, 5. So those would be our answers, 0, 3, and -2, -5. Now, in order to make sure that those are our answers, we need to verify them. And when we're verifying, we need to verify both solutions with both equations. So there's going to be a little bit more left side, right side work here. So starting off, we're going to have our left side, right side chart. Now you can write these as separate charts. You can write them all in one chart. Just make sure that you have all four solutions written out. So the first one here, we have 4x minus y plus 3 equals 0. So subbing in our first solution of 0, 3, we have 4 times 0 minus 3 plus 3 gives me 0 minus 3 plus 3, which is -3 plus 3. That gives us 0, so that one works. Checking the next solution, we have 4 times -2 minus -5 plus 3. We have -8 plus 5 plus 3, and that gives us 0. And 0 on the other side means this solution works. Now, we don't know if we're done until we've checked the other equation, because it can only be a system if it works for both equations. So our equation is 2x squared plus 8x minus y plus 3 equals 0. And we sub in our values. So we've got 2 times 0 squared plus 8 times 0 minus 3 plus 3 gives me -3 plus 3, which is 0. And checking our other solution, we have 2 times -2 squared plus 8 times -2 minus a -5 plus 3. Simplifying, we have 8 minus 16 plus 5 plus 3 gives me 0, and the right side was 0. So again, this works. So we have example 4. We're told that we have a system of equations here, and we're asked to solve using technology. That means that we're asked to use our graphing calculator. Now, when we're solving with our calculator, we still need to do a quick sketch just so that you have an idea where the intersection points are happening. So when we're solving using technology, again, the first thing we need to do is rearrange our equations so they say y equals. So this gives me y equals x plus 1. And my next equation is y equals -x squared plus 6x minus 3. Once we have our equations, we can graph them on our calculator. Now using our graphing calculator, we have y equals x plus 1 and y equals negative x squared plus 6x minus 3. We can graph those. Now if you want to make sure that you've got your standard settings, you're going to choose zoom 6. That gives you your nice 10 by 10 grid. And then we graph our parabola and our linear function. Now you'll see here we have two intersection points. So we're going to go second calc 5, enter, enter, enter. That'll give us our first intersection point at 1, 2, and then second calc intersect. We'll have to arrow to make sure we're closer to that second intersection point. Enter, enter, enter. And we have our solution of 4, 5. Now, once we have those, we're going to go back and sketch our diagram and label our points. So just doing a quick sketch here, we have our graph coming up, and we have our line coming through, and there's our two intersection points. Notice I'm not too picky about how this graph is set up. I'm not labeling any scales. I just want an overall sketch of the shape of the graph and where those intersection points are happening. So when we're labeling our intersection points, we have one here at 1, 2, and we have a solution at 4, 5. And so we can write those out. Two solutions, 1, 2, and 4, 5. Or we could say or there. Now again, we're asked to verify our answers using left side, right side. So this might be a good time to pause the video, try writing them out on your own, and then come back and check your work. All right, now taking a look at our verifications. For the first system, or for the first equation, we had a solution of 1, 2. When we substitute that in, we get 0 on both sides. For the next one, we subbed in 4 and 5, and again, we got 0. So negative 1 plus 1 is 0. And then looking at the second equation, we subbed in both solutions and again came out with left side and right side being equal to each other. Now let's move on to quadratic-quadratic. The methods are exactly the same, the graphs are just different. So for solving using technology, we're going to take both of these equations and set them equal to y equals. So rearranging those equations to equal y, we're going to have y equals 2x squared minus 16x plus 35. So we've moved the y across the equal sign, and we've brought the negative 35 over. For our second equation, we have y equals 2x squared minus 8x plus 11. Notice we're only changing the signs of the terms that have actually crossed the border. We have 2x squared minus 16x plus 35, and 2x squared minus 8x plus 11. Now when we graph those, we're going to have our two graphs. Both will be opening up. And it looks like we have just the one intersection point. Now if we wanted to be sure that there's not another one further off screen, we could zoom out. So zoom and then 3 for zoom out, hit enter. And we're still pretty sure that there's just the one intersection point. We could zoom in closer to that space using zoom box. I use this one quite frequently when I want to isolate just one particular section of the graph. And from there, we can find our intersection points. So once it's zoomed in here, we can see that there's just the one intersection point. All right, so doing our intersection here, we're going to have second calc 5, enter, enter, enter. And we have our intersection at 3, 5. So doing a quick sketch of our graphs, we have one parabola, and then we have another parabola that's just been shifted a little bit. And they intersect right here at 3, 5. And once again, once we have our graphical solution, we need to check or verify algebraically. Now in this case, because we just have the one solution, we only have one solution to type into each equation or to substitute into each equation. So starting off with our first equation, we have 2x squared minus 16x minus y, and that's equal to negative 35. So subbing in our values, we have 2 times 3 squared minus 16 times 3 minus 5 gives us 18 minus 48 minus 5, and that is negative 35. So that one works. But again, it's not a system until we've checked both equations. So we've got 2x squared minus 8x minus y should equal negative 11. Substituting in, we're going to have 2 times 3 squared minus 8 times 3 minus 5 gives us 18 minus 24 minus 5, and that gives us negative 11. So again, left side, right side balance, we know that 3 comma 5 is a solution. All right, so moving on to our last example, this is actually an application of systems. Normally at the start of this unit, if we were in class, I'd be showing you a clip from Cirque du Soleil, um, and showing you some of the acrobatic acts that happen. There's tons of articles out there explaining the math behind Cirque shows. This stuff doesn't just happen magically. There's someone who's planning it out and timing it out, and some of those things could relate to a system of equations. So for this example, it says, suppose that in one stunt, two Cirque du Soleil performers are launched towards each other from two slightly offset seesaws. The first performer is launched, and 1 second later, the second performer is launched in the opposite direction. They both perform a flip and give each other a high five in the air. The height above the seesaw versus the time for each performer during the stunt is approximated by the parabola shown below. So we're given a diagram here. We're shown that vertex, or that maximum point, is going to happen at 4.5 meters above the seesaws, and it's going to happen halfway between 0 and 1.5 seconds. So it's going to happen right here at 0.75 and 4.5 meters. Now let's take a look at what those systems of equations would be. So this is actually going back to a previous unit and just doing a little bit of review. So if we want to find the equations of these graphs, or the equations of these parabolas, we have to look at some key pieces of information. In both cases, we're going to use that equation y equals a times x minus p squared plus q. So we're using the vertex form. So for our first function here, our vertex is happening at 0.75 and 4.5. So I'm going to write that down. We have 0.75 and 4.5. And then we want to pick one other point on the graph. And I like to keep it simple, so I'm going to use 0, 0. Now, using our equation, we have y equals a times x minus p squared plus q. We're going to sub in the values that we know, and those would be 0 equals a times 0 minus 0.75 squared plus 4.5. Simplifying, we're going to have negative 4.5 equals 9 over 16a. And when we take negative 4.5 and divide by 9/16, we're going to have a equals negative 8. So our first equation is y equals negative 8 times x minus 0.75 squared plus 4.5. And for our second equation, again, we're going to have to find our vertex. So our vertex is happening halfway between 1 and 2.5. So that's going to be happening at 1.75. And our height is still at 4.5. So our vertex is happening at 1.75 and 4.5. And then we have our point. Now, again, I'm going to try to keep it simple. There's a point right here at 1, 0. Once again, we're subbing into our equation. We have y equals a times x minus p squared plus q. So we have 0 equals a times 1 minus 1.75 squared plus 4.5. Rearranging and simplifying, we have negative 4.5 equals 9 over 6a. And when we divide negative 4.5 divided by 9 over 6, we get negative 8. So for this equation, we're going to have y equals negative 8 times x minus 1.75 squared plus 4.5. And if you remember from our quadratics units, essentially these are the same graphs except that they've been shifted or translated. All right, so now we're asked to solve those equations graphically. So we're going to take those, put them into our calculator, and find our intersection points. All right, now graphing these equations on our calculator, we have negative 8 times x minus 0.75 squared plus 4.5, and then negative 8 times x minus 1.75 squared plus 4.5. When we graph these on our calculator, we want to make sure to use the window settings that represent the context of the question. And here we have a graph that shows us those window settings. In this graph, we're going from 0 to 3 for the x-axis, or for time, and we're going from 0 to 7 for height. So we can put that right into our calculator. We're going from 0 to 3, probably go up by 0.25, and then we're going from 0 to 7 and going up by 1s. And so when we graph this function or graph these two parabolas, it should look very similar to what's given to us in the diagram. Now to check our intersection points, we're going to go second, calc, 5, enter, 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 and we have our intersection point at 1.25 and 2.5. So we're going to go down and sketch our solution. So we have one taking off at 0. We have another one taking off 1 second later. And the two graphs intersect right here at 1.25 and 2.5. Now, if you want to label any of your key points, you certainly could. Here's 0, here's 1 second later. But most importantly, what we're looking at is that intersection point, is that they intersect at 1.25 and 2.5. Now, in our last question, we're asked to interpret the solution in the context of the question. So we have this intersection point of 1.25 and 2.5, but this is not just some function that I'm finding the intersections for. This actually relates to an application. So those numbers have significance, or they have meaning. So if we take a look at this, our graph was height versus time. And so this 1.25 represents time and the 2.5 represents height. So when this intersection of point occurs, it's happening 1.25 seconds after the first acrobat took off, because he took off at time 0, they intersect at time 1.25. So it's happening 1.25 seconds after the first acrobat takes off. And if the other one took off at 1, that means it's happening 0.25 seconds after the second one took off. And so this intersection point is happening right here. It's also happening 2.5 meters above the seesaw. All right, so 1.25 seconds after the first acrobat takes off, and 2.5 meters above the seesaw, the two acrobats intersect and high five. All right, guys, so we have quite a few examples here. Hopefully a lot of this is feeling like a review of grade 10, and that a lot of this will be kind of a refresher. The only thing new is that we're dealing with quadratics now instead of just linear functions, and we're going to be looking at some applications and some different intersection points in context. All right, have a great day, and we'll see you soon.